In this supplemental video, I want to focus on how we can calculate the ATP yield that we are getting out of the catabolism of fatty acids and compare it to carbohydrate metabolism. So if you haven't yet watched our videos for lecture 9 on the properties of lipids and fatty acids, as well as our pathways for breaking down fatty acids for generating chemical energy, I encourage you to watch these first before you focus here on how we can calculate the ATP yield based on these reactions. To start with, I want to remind us on the brief discussion I showed on one of the previous videos on the breakdown of fatty acids, comparing the energy density of carbohydrates and fatty acids. As we had concluded here, that because fatty acids are very rich in these alkane groups, as you can see up here in the structure of a fatty acid, we have these long hydrocarbon chains. These are very rich in energy because they're more reduced, right? These more reduced functional groups are higher in energy. So even though fatty acids have less of these different functional groups as compared to carbohydrates, they are higher in these alkane groups. Therefore, they have a higher energy density. So you actually get more energy out of these fatty acids. And so now to provide some evidence for this claim, I want to walk us through how we can actually calculate this based on the discussion we had on beta oxidation. So if you haven't watched yet the video on beta oxidation, please do so before you watch this, otherwise it will be difficult to follow. Let's look at these calculations. First, I need to remind us that we have different ATP yield coming from our electron carriers. FADH2 will deliver electrons to the ETC, the electron transfer chain, which we'll see in the next lecture, and is yielding 1.5 ATP, whereas NADH delivers a pair of electrons to the ETC2, but is yielding actually more, yielding 2.5 ATP. For now, we'll just let this stand. We'll see more evidence for this when we talk about the ETC. But this is what we're using for calculating how much ATP we're actually getting out of breaking down a fatty acid. What I want to do is just to take one fatty acid here as an example. So this is an 18-0, an 18-carbon fatty acid that is fully saturated, so has no double bonds. If you run this through beta oxidation, right, you need 8 turns. Have a look at the details in our other videos on how this works. Basically, right, you have 18 carbons, you run them all through beta oxidation, you're cleaving off per round of beta oxidation 2 carbons, you're ending up with 2 molecules of acetyl-CoA. Those don't have to go through beta oxidation anymore. So how you can calculate this, the turns, is that you simply take the number of carbons of your fatty acid, divide it by 2 and subtract 1. This is the number of rounds of beta oxidation that it will take. So in case of our 18-0 fatty acid here, it would be 8 rounds or turns of beta oxidation. What do we get out of this, right? We're doing 2 different oxidation reactions that we have now to take into account. So how much ATP are we actually making? First of all, out of our 18 carbon fatty acid, going through these 8 rounds of beta oxidation, we get 9 acetyl-CoA. Right? Dividing these 18 carbons in half, releasing 2 carbon acetyl-CoA molecules, we get 9 acetyl-CoA. If you remember our discussion on the TCA cycle, we're getting about 10 ATP per acetyl-CoA running it through the TCA cycle. This is combined from the 3 NADH that we are generating in the TCA cycle, making up 7.5 ATP, 1 FADH2 molecule for 1.5 ATP, and then 1 GTP, which is equivalent to 1 ATP. So every molecule of acetyl-CoA running through the TCA cycle will give you 10 ATP. So in this case, 90 ATP alone for the acetyl-CoA. Then in beta oxidation, we're also releasing per round 1 molecule of FADH2 and 1 molecule of NADH. So 8 for both, doing 8 turns of beta oxidation. If we're adding this up, we're getting 12 ATP for FADH2, and we're getting 20 ATP for NADH. Now, really important to keep in mind also is our activation step. We had discussed that we need 2 ATP to activate our fatty acid by condensation to our CoA cofactor, so we have to subtract this. So we get a total here for an 18-0 fatty acid of 120 ATP. On top of that, right, if you go from a total lipid, you also need to take into account the breakdown of glycerol. So remember our lecture 4 on where we had shown how glycerol can enter the glycolytic pathway, can be broken down. And so you get actually, in this case, additional ATP from the breakdown of glycerol through glycerol 3-phosphate, conversion to DHAP. DHAP can be run through the glycolytic pathway. We have our PDH reaction through acetyl-CoA that can run to the TCA cycle. This gives us a total of an additional 18.5 ATP. The way it breaks down is we actually have to subtract 1 ATP for the activation of glycerol. Then the step from glycerol 3-phosphate to DHAP is an oxidation. We're reducing NAD to NADH, so we get 2.5 ATP for this NADH. Then we're running the payoff phase for our DHAP, but only 1, so we're getting 2 ATP outright from substrate level phosphorylation and 2.5 ATP for the additional NADH that is generated in the conversion of our reaction 6 of glycolysis. Then from pyruvate to acetyl-CoA, that's our PDH reaction. Again, an oxidation reaction. We are generating NADH, giving us another 2.5 ATP. And then ultimately, as I've shown up here, we're getting 10 ATP for one of this molecule of acetyl-CoA to run through the TCA cycle. So if you're breaking down entire tags or lipids, you want to take into account the glycerol. For now, we just want to compare the fatty acid in itself. So keep in mind this number here of 120 ATP. Now let's compare this to the sugars. And we had done this already before when we talked about carbohydrate metabolism. Right? If we are comparing it to glucose, for example, right, running through glycolysis, our net ATP yield is 2 ATP. In glycolysis, right, we're running 2 of the payoff phases. We're generating 2 NADH in glycolysis, 5 ATP, 2 times 2.5 for NADH, another 2 for the 2 pyruvates that are resulting from glycolysis, runs through the PDH reaction, another 5. We are generating 2 acetyl-CoA in the PDH reaction, so 10 for each through the TCA cycle gives us 20 ATP. Adding all of this up is 32 ATP. Doesn't sound like a lot, but keep in mind, right, we just had broken down a C18 fatty acid, so we have to come up to the same carbon number. Glucose has only 6 carbons. So in order to really compare them, we need to use 3 glucoses. That brings us up to 18 carbons. So everything times 3. So out of the equivalent carbon numbers between glucose and the fatty acid, we get 96 ATP out of this. Right? So yes, fatty acids are more energy rich. We can actually see it here in numbers. Right? They are therefore a better energy resource, but keep in mind that carbohydrates are really released faster. Lipids are packed very tightly. It actually, as you have seen in the video on our fatty acid breakdown, it takes some work to actually break them down for energy. It takes somewhat longer. So they're really a complementary energy resource to our carbohydrates. The carbohydrates being more readily available to us, but a little bit less efficient in terms of energy density, whereas the fatty acids and the lipids are. And so they are more of a longer term major energy resource. The one major difference being the brain, some organs actually prefer and ultimately rely on glucose and not the breakdown of lipids. And the brain is one example for this. So this is how we can calculate the ATP yield and compare sugars and fatty acids. So I highlighted here, I really encourage you to work through these examples yourself. There are some examples given in your study aids. You can obviously cover them in the office hours too, but I would encourage you to first work them for yourselves, because I think it will really help your understanding of how these ATP yields work between fatty acids and sugars.